Okay, hello everyone. Let's resume our discussion now with gases. Okay, so now let's do the second example. Calculate the pressure exerted by each heel of a 100-pound woman in high heels if the area beneath the heel of each shoe is 0.250 inches squared. Okay, so in this case, we can assume that each shoe will divide the woman's weight. So we could use 50 pounds per force, but the heel then will then take that weight off of the 50 pounds. So actually, each heel is representing half of the weight of one shoe. So if there's two heels, there's going to be 50 pounds, and then the sole of the shoe is going to support the bulk of the weight of the body. So now it's going to be split in half. So that's 50 and 50. So in this case, we assume that each heel is going to be evenly distributed, as if we distribute the weight by four. Because if we have two shoes, two soles of the shoe, and that will divide the weight in half, and then the heel will further divide that weight, the other weight, in half, because there's two heels that's supporting the sole of the shoe. So we're going to say that the pressure equals force over area, and in this case, the force is going to be 25 pounds. And the area is going to be 0.250 inches squared. So you see here the area in both examples are drastically different because the area of a heel is much smaller than the area of the bottom of a shoe. Okay, so if we do this math here, we get a value of 100 pounds per square inch here. And see, that's over 20 times fold an increase in pressure that's being met by the floor. So it's not advised you wear heels. If you have hardwood floors, you're eventually going to damage the hardwood floor by repeatedly walking in heels. So probably not a good idea to try and look fashionable for TikTok or something at your home if you have hardwood floors. So don't do that. Okay, so I put this picture here. Oh, before we get to the picture, let's just do a checkpoint example here. So checkpoint. Example. Okay. So would um would a person wearing spike heels shoes. Well, a person wearing spike heel shoes or a person wearing sandals exert a greater pressure on a uh, hardwood floor. Okay. So you can pretty much gauge this by if you ever, test the sound of contact between a sandal on a hardwood floor and someone wearing spike heels. You would eventually, you would hear a very different pitch and sound, right? For someone wearing heels, because there's much more, there's a stronger force of contact. Well, not stronger force, sorry, stronger pressure due to the smaller area of the spike heel. So in this case, it would be a spike heel, and we could say smaller surface area of contact. Okay? Contact, oops. of contact. Whereas in the sandal, you have full contact with the surface of the sandal, so that area is going to be much bigger, so the pressure exerted is much smaller. Okay. So let's go back to this kind of view. This is what we call a YouTube, not the video sharing site, but an actual YouTube, and we can see here that water and ethanol, they exert different kinds of pressures. That's why the levels of them are so different. So water here will have, and that's because there's different densities. So we can usually say that the mass of the water times the sorry, not the sorry, not mass, but the density. So we could say dg. So when these tube stops moving, so this is density, this is gravity, and this is the height. So we say the density the product of this side of the equation will equal the product of this side of the equation, and that's because they have different densities. So say we have water here, and here we have ethanol. The densities will be different, and eventually these two liquid levels will remain constant. They won't no longer change, and that's because they're exerting the same pressure. So we can also compute pressure using this equation. So in this case, gravity is the in physics, the universal gravitational constant, the force, 9.8 meters per second squared. And then what's different here is the densities, and they will have a different height when they're put in the same U-tube. So we can also calculate densities using this equation. So they will kind of balance each other out based on their densities in this U-tube here. Okay, so that's kind of an introduction to like pressures exerted by water by liquids in a closed in a container. Okay. All right. So let's move on now to atmospheric pressure. So atmospheric pressure, Torricelli described an apparatus that's shown to the right. So this is how we measure pressure. So we have mercury, and so we can measure the pressure in the atmosphere to eventually where the mercury stops rising in this apparatus here. So when the liquid level of mercury stops rising, that means the pressure exerted from the atmosphere is equal to the pressure exerted from the mercury due to gravity. Okay. All right. So what we can say is, so we say the pressure, then we usually here there'll be we can measure how much the mercury level has risen into the tube, and that gives us a sense of the pressure of the atmosphere. And usually we record that in millimeters of mercury, as we see here. So we call this millimeters of mercury, like that. Okay. So instruments like this are called barometers, and they're used to measure atmospheric pressure. So usually, if you have, I forget, I think it's low pressures. You have precipitation, or you have bad weather, and then high pressure is where, So when it's or I think it's high pressure. Yeah, one of those two. But if you think about like kind of like in the atmosphere, when we have a decrease in atmospheric pressure, let me just verify this. So low pressure, low atmospheric pressure means means storms? Does it mean storms? I pretty think that it sure does. Okay. Yeah, so storms are usually caused by low pressure. So when the pressure is not is too low, you're going to get like a heavy storm or powerful storm. But also, I think when it's high, it's a let's see here. Yeah, when there's high pressures, that's where you get really extreme weather, like in like extreme heat when there's high air pressure, and that kind of makes sense because like the air particles are moving so fast they can't block the radiation from the sun. So that's why we get so high temperatures. And when there's not enough atmospheric pressure, um, you're going to get a actually when there's low air pressure, um, you're going to get more precipitation or more saturation of water in the air, and that's going to cause a storm. So really, really low pressure, when the air can no longer maintain that equilibrium with the natural air system, you're going to get a storm, pretty much. So that's kind of how you kind of relate atmospheric pressure. Okay. Okay, so usually on a normal day, if the pressure usually on a normal day is 760, around 760. So if it's really drastically different, like 240, 460, or like 1000, that's where we get some drastic weather changes. So the weather is actually very much impacted by the air system in the atmosphere. Okay. So we have the units of millimeters of mercury to record pressure. So that's usually what we report. If you open an app for the weather, the weather app, you might see inches of mercury instead, because in the United States we like the our system of measurement. We like to be different from everyone else. Okay, so we can also apply this kind of idea to this apparatus can also be applied to the concept of a like a water pump, like near a reservoir of water. So you crank the shaft of the water pump, and basically it creates a vacuum. It creates some empty space in the pump in the water reservoir, and that creates a vacuum. And and when you return it to the original position, you're going to expel, the water's going to rise up from the reservoir and expel that air that was removed when you opened the valve. So it's sort of like what happens is the atmospheric pressure is going to enter the system, enter the reservoir, and push the water up. So we use the concept of gas pressures here to kind of do everyday tasks as well. So it has a very important applications here. So that's why I kind of enjoy teaching this chapter, because it has a lot of things you can actually relate things back, and it kind of makes you think like, what if this gas has never existed? Like, how will life on Earth be different? Well, it'll be radically different, because we can't do some vital things that we do every day. So it's a very important phenomenon here on Earth, which makes it all the more wondering if the same kind of things can be achieved on Mars. Um, because there's much talk about kind of trying to terraform Mars, because we're trashing this planet, I guess. Well, once we trashed it, well, you know, depending on what happens, I might be forced to maybe try to combat where our Earth is headed. But um, as you see here, gases is kind of one of the big players here in the talk of global warming because we use gases to power our car, and eventually all the gasoline gets converted to molecules that are not very friendly to the environment. So we kind of tip the balance of what is a sustainable kind of chemical ecosystem. So all in all, we this talk about gases should kind of get people thinking about how it plays an important role in our everyday lives, and how it's kind of embedded in society, both politically and just society in society in general. But anyway, so that's how atmospheric pressure works. Okay, all right. Okay. So from this discovery, we named pressure unit in millimeters of mercury. So that's how it's been measured. There's no other way to. There's no like reason to do anything else than that. But that's usually how we measure mercury. So there's no reason to kind of change the standard because it's just how it's been done. So they also dedicated another unit called a torr. So you may see pressure units in torr as well, especially if you work in chemistry labs. Torr, atmospheres, bars. Bars is also used in, I think maybe in the car industry, but usually in the car industry, pressure is usually pounds per square inch or psi. So usually there's a lot of different units, and it depends on what industry pressure is used in. But they're all different, and it probably has its practical aspects too. So just it's probably just due to some just how how the industry has worked, and it just always used this unit. It's been set in stone, and changing it would cause like a catalyst, like a chain effect that would kind of maybe disrupt things. It may be hard to believe that, but I'm not really sure. Okay, so we also use torr. So 1 millimeters of mercury is 1 torr. So 760 torr equals 760 millimeters of mercury. And we define that as 1 atmosphere. So 1 atmosphere is defined as atmospheric pressure. So any deviations from atmosphere is going to be in relation to greater than or less than 1 atmosphere. Okay. All right. So let's do pressure calculation. So hopefully this is familiar to everyone. So probably the only time you'll have to change pressure units is when you're either doing a gas law equation or the ideal gas law. So sometimes we'll give units in millimeters of mercury or torr, and you're expected to convert that to atmospheres. All right, so let's calculate the pressure. Calculate the pressure from 745.8 millimeters of mercury to atmospheres. Okay, so 745. Oops. Sorry, that should be 45. All right, so our conversion factor is right here. Let's circle our conversion factor. So we're going from millimeters of mercury. So we want to divide by 760 because 760 millimeters of mercury is equal to 1 ATM. So we're going to smaller units. We're going to a unit, the larger unit. So when we're going to the larger unit, that means 1 unit of it is going to be much more of the smaller unit. So in this example, 1 ATM is going to be 760 millimeters of mercury. So we're going to divide. One atmosphere. Okay, so remember, conversion factors are exact numbers. They do not play a role in sig figs, so we're going to cancel out our millimeters here, and we will round our answer to 4 sig figs. 4 sig figs. Okay, then this will have infinite. All right, infinite number of sig figs. So we get 0.9813 ATM. All right. Okay, so that's we'll stop there for this video and pick it up in the next one, and we'll talk more about some other pressure units, and we'll start talking about gas laws or how we use this in terms of chemistry and the chemical industry. Okay, so see you soon. See you then. See you in the next video.